In this video, we will look at expressing equations of planes in the 3D space. Unlike the equation of a line, there are three forms which we can express the equation of a plane in, and we have to be familiar with each form and how to convert in between them. The first form is very similar to the vector form of the equation of a line. However, in planes, this form is called the parametric form, and it is not as useful. To understand how this parametric form is derived, we start from an arbitrary plane which contains a known point A, and it is parallel to two vectors d1 and d2. We let a random point on the plane be point R. To move from point A to point R, we simply have to displace point A by multiples of d1 and d2, or both, and all these different point R's will form on the plane. Thus, the position vector of point R can be used to describe any point on the plane and is used to represent the equation of the plane. The nomenclature is similar to the equation of a line in vector form, except that in the naming of planes, we usually use pi instead of L, and we have introduced an extra parameter mu as a second multiple of the second direction vector d2. In example 1, we are asked to write down the equation of a plane, and this plane contains point A with coordinates of 1, 2, and 3, and it is parallel to two vectors, number 1, 2, 4, negative 5, and number 2, 3, negative 4. And therefore, we can say that the equation of the plane in parametric form is pi such that r is equals to 1, 2, 3 plus lambda 3, negative 2, 4 plus mu 2, 4, negative 5. And we of course have to mention that lambda and mu are both real numbers. In example 2, now we are asked to form the equation of a plane that contains 3 points. We have point A, 1, 2, and 3. We have point B, 1, 1, and 1. And we have point C, 3, minus 1, 2. To form the direction vectors that are parallel to the plane, we can either use vector BA, vector CB, or vector AC. It does not matter which two of the three vectors that we choose, as long as the vectors that we choose are parallel to the plane. So therefore, I'm going to choose vector AB and vector AC. So for vector AB, it will be 1, 1, 1 minus 1, 2, 3, which gives me 0, minus 1, minus 2. And AC will be 3, minus 1, 2, minus 1, 2, 3. And this gives me 2, minus 3, minus 1. And therefore, the equation of the plane will be pi r equals to any point. I can choose point A or point B or point C. Let me choose point A. 1, 2, 3 plus lambda 0, minus 1, minus 2 plus mu 2, minus 3, minus 1. And we must always include that lambda and mu are real numbers. In planes, unlike lines, the vector form of the equation of a plane is not the same as the parametric form. Earlier, I have mentioned that the parametric form of a plane is not a very useful form. And the reason is because in order for us to form the parametric equation, we can simply use any two vectors that are parallel to the plane. And there are infinite number of vectors that are going to satisfy this condition. And therefore, this means that the equation in parametric form is not a unique one. And as mathematicians, we would like to work with equations that are more unique. Thus, we have the vector form of the equation, which uses, instead of the two direction vectors, a vector that is perpendicular to the plane. This vector is called the normal vector. And for any plane, there is only one direction that the plane is perpendicular to. That means the normal vector is a unique entity that we can use to describe the orientation of a plane. To define the plane using its normal vector, we will first form vector AR. So I can say that vector AR must be equals to R minus A. And I know that since vector AR lies on the plane, it must be perpendicular to the normal vector. So AR is perpendicular to the normal vector. And this means that AR dot N must be equal to 0. And therefore, we have R minus A dot N equals to 0. And we can expand this dot product. R dot N minus A dot N equals to 0. And if we rearrange this equation, we will end up with R dot N equals to A dot N, which is the vector equation of a plane. In example 3, we have the same plane as in example 1, but now we need to express it in vector form. And for us to do that, we will need to first find out what is the normal vector. And to find the normal vector, we will need two vectors that are parallel to the plane, which are given over here. And we have to do a cross product between these two vectors. So I have n equals to 2, 4, negative 5, cross product with 3 minus 2, 4. And this cross product becomes 6, negative 23, negative 16. Now, with the normal vector and also with this point over here, I can easily evaluate what is the vector form of this plane. So it will be R dot N equals to A dot N. And for the right hand side, we can evaluate what is this dot product. And this gives us negative 90. And therefore, I can say that R dot 6, negative 23, negative 16 equals to negative 90. This is the vector form of the equation of this plane. The last form is the Cartesian form. This form can easily be converted to and from the vector form, and it is useful when we are required to solve for intersection between planes, since we can easily key the equation of the plane into our GC to solve simultaneous equations. To convert from the vector form into the Cartesian form, we simply have to write the vector r as x, y, z and perform the dot product to simplify. For example, if I have the vector equation of the plane to be r dot 1, 2, 3 equals to 4, I can rewrite it as x, y, z dot 1, 2, 3 equals to 4. And if I expand this dot product over here, I will end up with x plus 2y plus 3z equals to 4. And this would be my Cartesian equation of the plane. In example 4, we have the same plane as in example 2, but now we need to express it in Cartesian form. So in order for us to form the Cartesian form, we will need to have the direction vectors that are parallel to the plane so that we can find out the normal vector. Okay, so for the vectors that are parallel to the plane, I'm going to use AB, which is 0, minus 1, minus 2, and AC, which is 2, negative 3, negative 1. And I can do a cross product to find out the normal vector. 0, minus 1, minus 2 cross with 2, minus 3, minus 1. And this cross product gives me negative 5, negative 4, 2. Therefore, I'm going to form the vector equation first. R dot minus 5, minus 4, 2 equals to 1, 2, 3 dot with minus 5, minus 4, 2. And if I evaluate this dot product, it will give me negative 7. And therefore, I can say that the equation of the plane is going to be minus 5x minus 4y plus 2z equals to minus 7. Or, if I don't like the negative signs, I can also say that it is 5x plus 4y minus 2z equals to 7.